Bismillahirrahmanirrahim. Assalamu alaikum. This is our 22 lecture of Advanced Electromagnetic Field and Waves, and in this lecture we are going to discuss scattering and diffraction, okay, which is chapter number 10 of book Jackson. So basically we are starting this chapter to describe different things like the closely related topics of scattering and diffraction we will discuss, which are the important in many branches of physics. Okay, you know that scattering and diffraction is very important in physics branches. Basically our approach depends on the relative length scale involved. Okay, how relative length involves the wavelength of wave on one hand and the size of the target on the other hand, because you know some of the wave is incoming and the wave has some wavelength, and they have to strike some obstacle, and that obstacle must have some size. So basically that we are dealing with the scale of the wavelength and the scale and the size of the target, which is the obstacle. So how they scatter or diffract on the other. Okay, when the wavelength of the radiation is large, you can say when the wave which is coming, okay, and if the radiation is if wavelength of that radiation is large as compared to the dimension of the target, means if target size is small and the wavelength is large of incoming radiation, a simple description in term of lowest order induced multipole is appropriate. So we use multipoles. What we use multipoles if the wavelength is greater than the size of the obstacle. Okay, and when the wavelength and the size are compatible, means both are same, what would happen then? A more systematic treatment will with multipole field is required. We use the multipoles, but a more systematic treatment. Okay, in the limit of very small wavelength, if you suppose wavelength is small as compared to the size of the target, now the size of the obstacle target is large, semi-geometrical method can be utilized to obtain the departure from geometrical optics. So we use the other treatments like as I mentioned you that geometric methods. Okay, we begin with the longer wavelength first of all in this lecture, in which the incoming radiation is long as compared to the size of the target obstacle. Okay, so let's start our today's topic, which is upon that scattering at longer wavelength. Means your wavelength has longer as compared to size. So what happens in this case? The scattering of the electromagnetic basically waves by system of those individual dimensions are small, okay, as compared to the wavelength is common and important occurrence. So basically in such interactions it is convenient to think of incident radiation field as inducing electric and multipoles. Okay, means it has both electric as well as the magnetic multipoles. An electric pole then we define as pxt, which is px e power minus iota omega t, whereas your magnetic multipole described as mx e power minus iota omega t. Okay, basically that oscillates in defined phase relationship with the radiation wave and the radiate energy in the direction. What happened in this scenario? A longer wavelength radiation will come on your obstacle which has electric and magnetic response in that medium, and whereas electric response is this and magnetic response is this. Okay, and when its wave strikes with the obstacle, what happens? It oscillates, the dipole oscillates. As the dipole oscillates, it produces radiations, it radiate. Okay, so now in that scenario, your incident electric field can be denoted by this epsilon naught e power iota k and naught x, where epsilon naught is basically the polarization, okay, and this e naught is basically the amplitude. Similarly, your incident magnetic field can be defined as n naught cross e incident by z naught. Okay, so this is your expressions. Now what is the electric field of electric dipole? As we mentioned, as we derived a relation in our previous, let me show you that this is the relation which we find after derive the relation of this magnetic vector potential in electric field. We got a final relation, and this is our relation. for far region, because our wavelength is light for far region, okay, where your kr is very very greater than 1, our relation is this. This our relation. So with this we have to use here for electric dipole. So this is for electric dipole. And for the case of magnetic dipole, it is minus k square by 4 pi without epsilon naught. By using wave duality principle, you can convert electric field into magnetic field and magnetic to electrical, and your dipole also convert, like P must be equals to m by c, where P is the electric dipole and m is the magnetic dipole. So by using the duality principle, you can convert your electric dipole to magnetic dipole, and your magnetic dipole is written as this. So you have to find the scattered electric field. So scattered electric field is basically the sum of electric dipole plus magnetic dipole. You just have to add both these. After adding these common outside and inside, you have to add. Now what you have to do, you have to take epsilon naught common. Once you take epsilon naught common, these factor cutting out and it remains n cross m by c. So this is basically the electric field scattered. Now, to measure the size of the obstacle, how you can find, you have to use the diffractional scattering cross section. What is diffractional scattering cross section? Which is basically the power radiated in the direction n with polarization E. This n is basically the direction, and this epsilon is basically the polarization, as I mentioned you before. Okay, per unit solid angle. Okay, per unit incident field in the direction of n naught, where polarization is E naught. So this quantity is known as the diffractional cross section. So how you can define the diffractional cross section to find the size of the obstacle? So this is basically d omega by d sigma by d omega, which is equals to dp scattered by d omega, dp incident by dA. Okay, so whereas your d incident by dA, dp incident by dA can be written as 1 by 2 real part of n naught E incident cross h star incident. Okay, where you know that E incident is, which I mentioned you before, what you have to do, you just have to multiply E naught star before this. So once you multiply E naught star this, so E naught, what it becomes, E naught becomes E incident, and this vanishes. So E incident now becomes E naught star E in multiplied by E naught. Similarly, now what you have to do, you need h in, then you have to take this star, then you finally you have to multiply E in cross h in. So we know that H in, as I mentioned you before, can be written as this. So H in is N naught E in by Z naught. E in we already find, but by Z naught we need E in H in star, because in formula is H in star. So you have to take star only. So complex, so it becomes star here divided by Z naught. Now final term is what you have to do. You have to find dP in by dA, 1 by 2 real part is as it is, and inside is the cross product of E in by H star in. So you have to multiply H star in multiply by H in. So after multiplying, you can see that E naught star and E in whole star and E naught star E in simple. So simple plus their star becomes their conjugate, their square. Okay, mod square, and E naught cross multiply E naught star must be equals to 1. Okay, so you can see this is our final expression of dp in by dA. Now we have to, what we need dp scattered by d omega. Once we get this, we divide and we will get our diffractional scattering cross section. So we need now dp star by d omega. Similarly, as you find this, so this is very similar, but the factor r naught is here, because you have to integrate our whole solid angle. But when area, so there is no 4, because area, you know that 4 pi r square, that's why r square is contribute here. But here is the solid angle, only 4 pi, there is no r square, so r square goes to the other side. Okay, so only term of r square as it is, and now it becomes E scattered and H scattered star. So final relation is similar, but here in instead of E naught it is only E star, and instead of E in it is E scattered. Okay, so now you just have to divide. 1 by 2 cancels with 1 by 2, only r square remains, and Z naught cancels with Z naught, only this and this left. This is E naught star E scattered, E no sorry, this is not E star scattered, and E naught star E incident whole square. And in denominator, this factor E naught star E in must be equals to E naught square. Now you need to find up in numerator find this expression. Once you find this expression, put it and you get your final diffraction scattering cross section. Okay, so here you can see we have to find in numerator term, which is the E star multiplied by E scattered. We already find E scattered, as I mentioned you before. This is our E scattered. We just have to do is that we have to multiply our E star with E scattered. So E star multiply with E scattered. So what constants remains outside? E star multiplied by this term and E star multiplied by this term. Where this is A cross B cross C, you have to use the identity where you know that A cross B cross C can be written as first A cross C, B outside, and then B cross C, A outside. And there is another property A dot B cross C. It can be written as one time B outside, C cross A, one time C outside, A cross B. Okay, so you have to use the vector identities here to solve. Okay, so how you can solve this? Simply A cross C means n dot n becomes 1, P outside, and B cross C means P dot n, P dot n, which is P, you know that n is the direction, P is basically the polarization, their dot product must be equals to 0. Plus you have to use this identity where this is B, this is C, and this becomes A when you use this identity. So you can use this identity with in replacement of this. So you have to C outside means M by C outside, A cross B. A is basically E naught star cross N. But you here see it, I just replace by N cross E naught star. So if I replace, so I should have to initialize minus sign outside and minus, and there this minus becomes plus. Okay. So this is 0, this is 1. So E naught star P plus N cap E naught star cap M by C. Okay, now there is a square upside, so you have to take the square of the expression. So E square becomes K square becomes K4, and this whole term square and this whole term square. Finally, what you have to do, this expression divided by this expression, and this expression answer is only E naught square. So the final answer is same, but here E naught is added. Okay, so this is your diffractional scattering cross section. Okay, so this is how you can find basically this cross section which I mentioned you, that this K4 divided by 4 pi epsilon naught E naught whole square E star cross dot P plus N cross E star multiplied by M by C whole square. Basically this dependence of cross section you can say that on N naught and E naught. Okay, on N naught and E naught, which implicitly contained in the moment of the dipole, which I mentioned you. P is the electric dipole and M is the magnetic dipole. Basically the variation of the diffractional and total scattering cross section with you can see here wave number K4. If the wave number is K4, so it means the wavelength is lambda power minus 4, because you know that k is equals to 2 pi by lambda. So if k is 4, so lambda is minus 4. So if lambda is minus 4 means frequency is power of 4. Okay, it is almost the universal characteristic of scattering of longer wavelength. If scattering at longer wavelength, like you see in skies, longer wavelength, okay, the radiation is coming very long distance in skies. Okay, in sky you can say so that's why this dependence of frequency is known as the Rayleigh law. This frequency dependence is known as the Rayleigh law, whereas frequency power 4 dependence at longer wavelength. Only if both the static dipole moment vanish does the scattering fail to obey Rayleigh law. Okay, the scattering is done via quadrupole or higher multipole or frequency dependence dipole moment and varies omega power 6 or higher. Sometimes the dipole scattering is known as Rayleigh scattering. This dipole scattering is basically known as the Rayleigh scattering, but this term is usually reserved for the incoherent scattering by a collection of dipoles scattered. So this is all about the scattering cross section, whereas you know that the scattering dependence of frequency, scattering cross section depends upon frequency, as I mentioned. That's why the sky terms blue, because the blue has the longer Blue has more frequency, that's why they scatter more in the sky, which term sky as blue. So this is how you can find the mathematical expression of sky blue. So that's all for today. In next lecture we are going to solve one of the example like scattering by a small dielectric sphere. Till then, take care. Allah Hafiz.